The next is a numerical based on the Arrhenius equation. On the basis of the Arrhenius equation, we use generally two formula. The first one is a log of k is equal to log of a minus EA upon 2.303 RT. The other formula which we use is log to the base 10 K2 upon K1 is equal to EA upon 2.303 R in bracket T2 minus T1 upon T1 into T2. While using this formula, the thing which is to be kept in mind is that T2 is always greater than T1. So the temperature which have the higher temperature should be considered as a T2 and the lower temperature should be considered as a T1 when I'm using this formula. So here the question is, for a reaction specific rate constant at 283 Kelvin is this much and at 293 Kelvin is this much, means this is going to be T2 for me and this is going to be T1 for me. So ultimately this will become K2 and this will become K1. So the formula which I will use is going to be this one. We have to calculate the energy of activation, that means EA we have to calculate. So here I will use this formula. The formula is log to the base 10 K2 upon K1 is equal to activation energy, that is EA upon 2.303 R in bracket T2 minus T1 upon T1 into T2. So here the log to the base 10 K2 upon K1, K2 is 2.5 into 10 raised to minus 5 upon this is 2.25 into 10 raised to minus 6. It is equal to activation energy we have to calculate upon 2.303. R is 8.314 into T2. T2 is 293 minus 283 upon 283 into 293. So after all this, this 10 raised 2.5 into 10 raised to minus 5 can be written as 25 into 10 raised to minus 6, 10 raised to minus 6, 10 raised to minus 6 will get cancelled. And the left will be 25 upon 2.25, which gives 11.111. So, and the log of 11.111 is 1.04575. So this will 1.04575 equal to activation energy into this will give you 10 upon 2.303 into 8.314 into 283 into 293. Activation energy this 10 and this will get cancelled and we will get 28.3. So activation energy, that is EA is equal to 2.303 into 8.314 into 28.3 into 293 into this number. The log is again in a formula, so no need of calculating anti-log, into 1.04575. After all multiplication, you will get a number 165941. Answer will be in a joule because R is taken as 8.314, which can also be written as 165.941 kilojoule. So this is the activation energy with this data. So second numerical, the two reactions of same order have equal pre-exponential factor, but their activation energy differ by 24.9 kilojoule per mole. Calculate ratio between the rate constant of these reactions at 27 degrees Celsius. So now in this case, we have to calculate the rate constant ratio, that is the K1 upon K2. And in the question it is activation, the difference in the activation energy is given, that is 24.9 kilojoule per mole. So let's solve the question. Suppose I have log to the base 10. Now here we have the difference between the activation energy and the reactions are different, but they are of same order and having a same exponential factor. So I cannot use that formula log to the base 10 K2 upon K1 is equal to EA upon 2.303 because that formula is applicable only when the reaction is same and we are just changing the temperature. But in this case, the reaction itself is a different. So we have to make a new formula over here. So we have the Arrhenius equation, log of K is equal to log of A minus EA upon 2.303 RT. Now for the first reaction, it will become log to the base 10 K1 is equal to log exponential factor as it is written same. Activation energy is different, so for first upon 2.303 RT1 and then log to the base 10 K2 is equal to log of A minus again the activation energy for the second is equal to 2.303 RT2. We have to find the ratio of the two reactions. Being a log, the subtraction will ultimately get converted into the ratio. So let us subtract this minus this, that means log of K1 minus log of K2. So if I am subtracting, so log of K1 minus log of K2, since exponential factor is same, so log A will get cancelled and we will have minus EA1 upon 2.303 RT, and due to this subtraction it will become positive, so plus EA2 upon 2.303 RT2. So we will have log to the base 10 K1 upon K2 finally is equal to, something is common, the common terms are 1 upon 2.303 RT in bracket, here EA2 minus, I can write EA1. So log to the base 10 K1 upon K2 it is equal to EA2 minus EA1. It is given that difference is 24.9 kilojoule per mole. This is kilojoule per mole, so it can be written in joules. It will become into 10 raised to 3 upon 2.303 R, that is 8.314 into temperature. Temperature is 27 degrees Celsius. When if I am converting it into Kelvin, then plus 273, that is 300 Kelvin it will be. So into 300. So I can say that log to the base 10 K1 upon K2 is equal to, this after all calculation you will get 4.3421. Therefore we can say that K1 upon K2 is equal to anti-log of 4.3421, which is equal to 3421. Anti-log of 3421 is equal to 2198. So it is 2.198 into the characteristic 10 raised to characteristic, that is 10 raised to 4. So this is finally the ratio of K1 and K2. So in this question, since the reactions are different, so we make another formula for the different reaction. Okay, now the question number 3. A very simple question. It is given that for a reaction A plus B gives C plus D, delta H value is given as 20 kilojoule per mole. The activation energy of the forward reaction is 85 kilojoule per mole. Activation energy is this for the forward reaction. Calculate the activation energy for the reverse reaction. Both are given in kilojoules only. So delta H, it is given as 20 kilojoule per mole. Activation energy for forward reaction, it is 85 kilojoule per mole, and activation energy for the reverse reaction we have to calculate. So we have a relation that delta H is equal to activation energy for forward reaction minus activation energy for reverse. So this is going to be minus delta H. So forward reaction is 85 minus 20. So we will finally have 65 kilojoule per mole. That is activation energy for the reverse reaction is 65 kilojoule per mole. Now the numerical based on the complex reaction. In this case, the reaction is given to you, will be given to you as well as their mechanism. So by observing the mechanism, generally the question is asked for the rate law, that write the rate of the reaction. That is, you have to write the rate law for the reaction. So we have a reaction 2 moles of NO plus Cl2 gives 2 moles of NOCl. This is the main complex reaction, and this main complex reaction is taking place in the two step. That is, first step NO plus Cl2 is giving NoCl2, and in the second step NoCl2 combines with the NO and produces 2 moles of NoCl. Now in this case, this NoCl2, it is formed in a first step and get consumed in the next step, and that's why it is considered as an intermediate. So sometime the question may be asked for the intermediate. So the substance which is formed in a one step and get consumed in the other step is called intermediate. Now we have to write the rate law. The rate law for the reaction, the rate law of the reaction, that is the rate law for the main reaction, we have to write. As we know that the rate of a main reaction depends on, or the rate of a complex reaction depends upon the rate of slowest step. Out of these two, this is the slowest step. That is, I can also use the word rate determining step. So rate of the reaction will depend upon the rate of this slowest step. Now this slowest step is now the steps which are involved in a mechanism are considered as elementary reactions, and we are able to write the rate law for elementary reactions, as in elementary reactions the powers are nothing but the coefficient. So if I'm writing the rate law for this reaction, so for this reaction rate law will be rate is equal to K into molar concentration of NO and molar concentration of Cl2. The power is 1 1, so the coefficient is 1 1, that's why the power will be also 1. So I can say that this is a rate law for the slowest step, and being a slowest step rate law, therefore this will be the rate law for main reaction also. So rate law for main reaction is going to be same, that is rate is equal to K into NO into Cl2. So this is the first one. Now the second question. The reaction 2 moles of NO plus Br2 gives 2 moles of NOBr. Obey the following mechanism, thus and thus. Suggest rate expression. Now in this case, the thing is to be observed that the first step is a fast step and the second step is a slow step, right? So if I'm writing the rate law for the slowest step, so rate law for the slow reaction is rate is equal to K into molar concentration of NOBr2 and molar concentration of NO. Now here I can say the rate of a reaction is this is the rate law for the slowest step, and the rule says that the rate law for the slowest step is the rate of a reaction, and the rate of a reaction is this. Here the reactants are NO and Br2. Here it is the main reaction and the reactants are NO and Br2. So the rate law, if I'm writing the rate law for the main reaction, then it should be in terms of the reactant of the main reaction, that is NO and Br2. Rate law should not be in terms of intermediate. But here, as I said, the rate of a main reaction depends upon the rate of slowest step, and this is the rate of slowest step which involve NOBr2 also. So by default, this should become the rate of the main reaction. But as I said, the rate of a main reaction should have only the concentration of the reactant which is present in a main reaction, that is NO and Br2. So somehow we have to replace this NOBr2 from here. So rate of a main reaction is, as I said, the rate of a complex reaction will be also equal to the rate of slowest step, that is NOBr2 and NO. But as I said, we have to replace this NOBr2. So for replacing NOBr2, we will find that how many NOBr2 has been formed in a reaction. So NOBr2 is forming a first step. So from the first step, we can write reaction is a reversible. So we will have an equilibrium state. So Kc is equal to, we will have the concentration of NOBr2 upon concentration of NO and concentration of Br2. Here I want the concentration of NOBr2 in the expression. So NOBr2 will be equal to the concentration Kc into concentration of NO into concentration of Br2. So instead of NOBr2, I can write the constant Kc into these two. So the rate will become K into Kc. Instead of NOBr2, it is NO into Br2 and then this NO. So finally we will have k into k, see both are constants, so I'm just replacing this by k dash. NO into NO will give you NO whole square into Br2. So for this particular reaction, the rate law is going to be this. So always keep in mind that if the rate of reaction, the rate of slowest step involve intermediate, then always substitute the value, or always substitute the value of the concentration of that intermediate, because the rate of main reaction should be in terms of their own reactant, that is a main reactant. Like here the main reactants are NO and Br2. Such problem was not here, because the here in this case the first step was the slow step, and the first step is a slow step means there is a no intermediate only.